quick, we're going to go over normal forces and do another problem with tension. And I'm not going to go into huge amounts of detail about normal forces, but the important thing is anytime objects are in contact, technically the contact forces are normal forces. They're two objects in contact. Now, there are other forces that occur when objects are in contact, say friction. And we'll get into friction at a later point. But for the moment, we're going to ignore friction. These are contact forces, and they are perpendicular to surfaces. Now, that doesn't mean that they're straight up and down. That means they're perpendicular to a surface. If I have a surface like this ruler, right now, it's nice and horizontal, and so my normal force would be that way. But if I rotate it, then the pin acting as the normal force has to rotate with it. And it comes up to, if I have, say, a wall and someone leaning against it, then this has a normal force by the wall on the person, let's say. Right, so normal forces, the direction is always perpendicular, right? So perpendicular, another word for perpendicular is normal. Or another word for normal is perpendicular. But they're always called normal forces. And I'm not altogether certain why, aside from the fact that these words in physics are basically interchangeable. All right, so these are going to be our normal forces. So, that said, here's a problem. We have a block sitting on a ramp, and this ramp is tilted. So this is a 30-degree incline. And we have a 60-kilogram block, and we have a rope that secures it to the top. So say this is a setup where we're going to burn through this rope, and then this block slides down the ramp, and we time or measure its velocity in some way. So we're trying to figure out something. And we're also going to say this is frictionless. All right. So how do we attack a problem like this? We don't actually even state what the problem is yet. Let's state what the problem is. We want the tension in this rope. All right. So in all the homeworks that are assigned this week and in the upcoming homeworks, you're going to have problems where you have tensions defined, and you're going to have problems where you have forces that are not along your normal XY axes, which you notice I'm not drawing in at the moment. We're going to wait until we draw the free body diagram, because it doesn't matter what the positive direction is yet. It matters when we start writing down how to do the sum of the forces. So over here, we'll do the free body diagram. And the first thing we can put in immediately is that this thing is an object with some weight. So we'll put that in. And weight force by the earth on the block. So we'll call this the block. Then we have a normal force. There's a surface in contact right there. So we have a normal force acting on this block. And it's not straight up and down. It's at an angle. So we can put in the normal force by the, we'll call this the slope, by the slope on the block. Now, if we want to, we can gently put in that there is an angle here that's 30 degrees. You can kind of tell that maybe that's true. We'll go into a proof of that very quickly here. Now, there's a tension, and this rope is parallel to the surface. So we can put this in And that's going to be the tension by the rope on the block. And these should be perpendicular because this normal force will be perpendicular to the surface and the tension force will be parallel. So we can put in that that is a right angle. So I want to prove that this angle is 30 degrees, and I've got 8 minutes to do it because I have an appointment at 5 o'clock, and it's 4:52. So when we have this geometry, right, so we have, I'm going to draw it over here. Let me zoom in. There you go. So there's our vertical. Here is our slope. This is 30. This has to be 60. Because these are two straight lines that are crossing, this opposite angle is 60 degrees. If I put in a perpendicular here, so this is absolutely perpendicular, then these three angles have to add up to 180, or these two have to add up to 90. This is 30 degrees. And then this dotted line and this vertical line says that this is 30 degrees. Now that's important when we go do other problems. Is when I go over here, we wanted to show that this was 30 degrees. What we're doing is saying the weight force is along this line. The normal force is along this dotted line, and the tension is along the slope. So that's that is our three lines. That's the important thing of, we'll visit this in more detail later if you have questions. But the gist is, for every force, we can extend the vector, be long lines, and then we can show what these angles need to be. Okay. So we have this. This is our free body diagram. But we also need to put in directions. And if we put it in vertically, so off to the side in dashed lines, if that was what we did, we would have to find components for two forces. And physicists are lazy. Instead of setting the problem up like this, let's just rotate it. All right. Now we can set that the x direction is this way, down the slope, and the y direction is that way. Now that still has some consequences, is gravity is still pulling down that way. Now it's pulling at an angle. Right? Is gravity doesn't change because we've rotated a slip of paper. But that's going to be our direction. So that's all we're doing, is rotating our paper and effectively rotating our diagram. But now the thing that has components is the weight force. So there's our vertical component of the weight force. So I'll call that WY. And then there'll be a horizontal component that is WX. And you can see the triangle that's in here now. And this angle will be 30 degrees. So this is our opposite side. This WX is the weight times sine theta. This WY is the weight times cosine theta. That's going to be important, because now that lets us get to the tension. All right, so now I got to rotate this back so that I have some paper under me, and we can write some of the forces in our y direction is going to be the normal force, which is positive, it's upwards, and we're going to subtract out the y component of the weight force. And then the sum of the forces in the x direction is going to be the in the positive direction, it's going to be this weight force minus the tension. And the presumption in this problem is that these things are held together so that there's no acceleration and there's no motion in the thing. So we can write it as m times the acceleration in the y direction is 0. And this is the mass times the acceleration in the x direction, which is 0. So we're always going to make these two sorts of statements. The sum of the forces equals some forces equals the mass times acceleration, which might equal 0. We're always going to make statements that look like this. All right. And then we're just doing the stuff in the positive direction minus the stuff in the negative direction. But we don't actually care about this unless we asked what the normal force was. And if, because we're asked that, we can say, well, the normal force is the weight times cosine theta. Okay, that's easy enough. But this is what we want. Our tension is going to equal the weight in the x direction. So I'm going to go up here. Our tension equals the weight in the x direction, which is the mass times g. I should introduce the weight. Is the mass times g. So I probably have been assuming that for a bit. So hopefully you've been doing the reading. Mass times g times sine theta. And now we can calculate what it is. 60 kilograms times 9.8 meters per second squared times sine of 30 degrees. That's our tension. And our tension is now just a calculatable thing. 60 times 9.8 is 588 times the sine of 30 is 1/2. We get 294 newtons. And that's our answer. So if you're getting anything out of this, it's the setup to the problem. We draw a free body diagram and we choose directions that are convenient. We try to choose directions that are in the direction of the motion, and then we write out Newton's second law. We write out in the y direction what the forces are adding up, and then that they equal the mass times acceleration, and we solve for the thing that we want. And we also fill in if we know things like the weight force or that some tensions are equal. If we know other properties about the forces, we put those in as well. All right. So I'm sure you'll have more questions. We're going to do more videos, obviously, but I've run out of time for today. So, if you have questions, please email me. Right, realize you're on week 1 of forces, so we've got time to go over things. All right, it's not going to be as complicated as you might think.